Today, we're going to examine one of the most famous cycles in thermodynamics, the Carnot cycle. Unsurprisingly, the most efficient cycles are ones which do not involve any irreversibilities. The most widely used reversible cycle is called the Carnot cycle. This can be used in either a steady flow or a closed system. It is composed of 4 reversible processes. The first step involves a reversible isothermal expansion. This must occur slowly for the process to be reversible. And to keep the temperature constant, an amount of heat must be added, QH. As the expansion occurs, work is done on the surroundings. The second step involves an adiabatic expansion. Again, we have work being done on the surroundings, but now accompanied by a drop in temperature. The third step is a reversible isothermal compression. Now work is being done on the gas, which requires a release of energy, QL, to keep the temperature constant. The final step is a reversible adiabatic compression. The gas continues to compress, temperature increases, and the process ends with the gas in the initial state, thus completing the cycle. The entire cycle can be seen here on the PV diagram. We have isothermal expansion with heat added between 1 and 2, adiabatic expansion from 2 to 3, isothermal compression with some heat rejection from 3 to 4, and finally adiabatic compression from 4 back to state 1. The net work over one complete cycle is given by the area enclosed inside the PV diagram. So here's something to think about. Would it be better to compress the gas adiabatically instead of isothermally when we get to state 3? This would avoid the loss of heat, QL, and probably make this more efficient. If we did this, instead of going to state 4, we go back up to state 2. This would indeed avoid the loss of heat, QL. However, this would also produce 0 work, making the cycle essentially useless. It also removes a second reservoir, which violates the second law of thermodynamics, as seen 2 videos ago. What we just saw is called a Carnot heat engine. Heat, QH, is added to the cycle, and we get some useful work out. What would we need to do to turn this into a refrigeration cycle instead of a heating cycle? Since every process in the cycle is reversible, we simply just run the cycle in reverse. In this case, work is put in, some heat is rejected, QH, while the heat into the cycle, QL, is cooling the surroundings. This is then called the Carnot refrigeration cycle. This is shown in the PV diagram down here, which is exactly the same as the previous one, except that all the arrows are going in the reverse direction. Based on what we have seen in the previous 2 videos, there are a few requirements that must be satisfied for any cyclic device. There cannot be just a single heat reservoir, there must be at least 2, and any refrigeration cycle must involve some net energy input. These requirements have some interesting effects on the overall efficiencies of these cycles. The first of which is that the efficiency of an irreversible cycle is always less than the efficiency of the corresponding reversible cycle. And the second is that the efficiencies of any reversible cycle is the same when operating between the same 2 reservoirs. Proof of these can be found in the textbook. A heat engine that operates on the reversible Carnot cycle is called a Carnot heat engine. We have seen previously that the thermal efficiency of any heat engine is given by eta TH equals 1 minus QL over QH. For any reversible heat engine, the heat transferred is related to the absolute temperature. So this can be expressed as eta TH equals 1 minus TL over TH. Because the Carnot heat engine is made entirely of reversible processes, it must therefore have the highest possible efficiency. It can be seen on the previous slide that this is actually always less than 1, unless the 2 temperatures are the same, but then no work would actually be produced. Any real heat engine will have some kind of irreversibilities, and therefore have an even lower efficiency. Many real heat engines in operation today have efficiencies around 40%. This may not sound great, but remember that they can never get to 100%, even when all irreversibilities are removed. So it should not really be compared to 100%, but rather the maximum theoretical efficiency given by eta TH reversible, referring to the reversible efficiency. For actual heat engines, the efficiency will be maximized by having the greatest possible difference in the two temperature limits, TL and TH. Similarly, a refrigerator or heat pump acting on the Carnot cycle is called a Carnot refrigerator or heat pump. We saw the definitions of the coefficient of performance in the last video, as seen here. Again, here we can replace the heats with the temperatures in the reservoirs, so we get the second way to calculate the COPs for reversible processes. Similar to the efficiencies, the reversible versions of refrigerators and heat pumps are the most efficient, and therefore will provide the highest value of the COP for given temperature limits. Any real heat pump or refrigerator will inherently have some irreversibilities, and therefore have lower values of the coefficient of performance. And again, the COP of the real devices can be compared to their theoretical reversible counterparts to get an idea of how efficient they are. Having the smallest possible value of the low temperature reservoir, TL, will maximize the coefficient of performance for both heat pumps and refrigerators. So that is the end of the theory for this week. On to the pre-lecture example and the answer. As usual, please bring any questions you may have to class. See you later.